The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
You know, I didn't get to say in person to you how fun this class is, but the material itself is definitely the most exciting in all the 2W3 curriculum. I want to take a minute and just kind of reintroduce myself. My name is Sanjay Sarma. Please call me Sanjay, right? I'm very informal. I demand informality. I will be informal to you as well. I will learn all your names, trust me. How many people do we have in class? 130? Okay, I'll learn half your names. Okay, but we're going to have a lot of fun. Some of the classes are going to be videotaped because we're doing it slightly differently. This class is going to be a little more MIT than Harvard. In other words, we're going to do stuff in a little more formal, fundamental way. And it'll help us address and understand some of the concepts, especially in kinematics, more intensely than if you took it the way that it's taught in other classes. As I said, my style is going to be very informal. We're going to see who speaks. We want you to speak up. I'll ask questions. You will never, ever be penalized for saying anything in class. You'll only get credit for it, okay? Even if it's funny. Okay. So in the last class, we set up what we're going to do. We explained that in the field of dynamics, there are actually two pieces. There's kinematics and there's kinetics, right? And we said we would do kinematics in this class, and we're going to do kinetics afterwards. Kinematics is all about motion, and as I said, it's the most fun part of dynamics. So let me just lower this. Sorry. So there's no better way to get going than to simply start by writing out a problem and trying to solve it in class, and that's what we're going to do now. I can get this all lined up, focused. Okay. So the problem that we're going to start with is, imagine that I'm standing here in the corner of this room, okay? I have a Frisbee, and I throw it across the room. The Frisbee translates, that is, it moves, it rotates, and let's make it more interesting. There's an insect on the Frisbee, okay? And when the Frisbee is moving across the room and rotating, the insect starts running away from the center, okay? Now, this is a made-up problem, but this is the problem I'm going to solve today. And what does solving a problem mean? I'll solve a piece of it, but let's examine what this could mean. First of all, this is obviously a silly exercise, but if you imagine an astronaut on the space shuttle hurtling through space, this is a similar problem. And a question you might ask is, the astronaut's boots, let's say they're magnetic, exert a certain force on the space shuttle, right? Now, obviously, there are certain conditions under which the astronaut would lose contact with the space shuttle, assuming the surface of the space shuttle isn't iron, it's aluminum, so my example doesn't really hold, but that's okay. Okay, so assume it's iron. Why isn't it aluminum? Why isn't it iron? Because it's heavy. Yeah, we know. All right, but assume it's iron, right? So let's assume that the astronaut's holding onto the space shuttle using magnetic boots. Under what conditions would the astronaut stay in contact with the space shuttle? Anyone? Hi. Excuse me. Sorry. So, under what conditions would the astronaut stay in contact with the space shuttle? Space shuttle is swirling through space. It's hot in here, isn't it? Let's open the windows. I don't know if there's a way to do this. Go ahead. How does the astronaut stay in touch with the space shuttle? Okay, we'll figure this out. It's broken. Anyone? Raise your hands. Yes?
When the magnetic force that I'm supposed to see into the space shuttle is stronger than the force.
Excellent. Magnetic force is strong enough to keep him or her in contact and able to overcome whatever force is pulling him or her away from the space shuttle. What force is pulling him or her away from the space shuttle?
Inertial force. Centripetal.
Centripetal. What else?
Inertial force.
Inertial force. What's that mean? You're right.
It means that he advances certain motion.
Yeah.
By the fact that he has mass he wants to keep.
Yeah.
And,
Some more than others. Yeah.
He's going to keep that by his force is being exerted on his.
That's right. Look, it's very simple, right? Think of this astronaut. Forget the spaceship. Imagine, just imagine the spaceship isn't there, right? If you just think of the astronaut, this guy or this woman is hurtling through space, right? And he or she's doing it under the influence of a certain force. And that force had better be equal to mass times the acceleration of that astronaut, right? If the magnetic force cannot equal or exceed m times whatever the A is, bye-bye astronaut, right? Get it? Because the magnetic force cannot provide the cannot affect the change in momentum, rate of change in momentum required to keep the astronaut in position. Get it? So the magnetic force is weak and the space shuttle is kind of spinning away, right? If the force isn't enough to keep the astronaut spinning, accelerating with the space shuttle, so they're going to separate, right? So this problem of me throwing a Frisbee across the room, an insect on the Frisbee, running away from the center of the Frisbee, the practical application of the problem could be, hey, what is the attractive force? For example, spiders have adhesive pads, right? So what is the kind of the adhesive force that the spider should be able to exert if it wants to stay on the Frisbee as I hurtle it across space, and if it wants to kind of move on the Frisbee in some predetermined way? Get it? Now, in order for me to answer this question, what question do I need to answer first? In order to answer the question, what is the force required, right? Let's say I know the mass of the spider. What is the one thing I need to figure out? Yep.
Coordinate system you need.
Yes, that's how I start. And then what do I need to do? That's right. All you need to do is find the acceleration of this dude, the spider, as it stays on the Frisbee and tries to move as it's hurtling through space, right? That's all we need to do. And answering that question is the subject of a topic which begins with K, which is kinematics, right? Okay. All right. So how do you do it? How would you do it? Where do you start? Say it again. Okay, and then what do you do? Very good, right? Look, if I'm sitting on the Frisbee, let's say I'm sitting on the Frisbee, I'm the pilot of the Frisbee, right? And I see my buddy, the astronaut, trying to move on the space shuttle, right? Or similarly, I'm sitting on the Frisbee, and I see this insect, the spider, running away from the center of the Frisbee. With respect to myself, what's the spider trying to do? In a what sort of path? Straight line, right? That's where I'm concerned, just moving away in a straight line, right? What about with respect to the ground observer of the space shuttle? Or with respect to me, what's the spider doing? Yeah, it's kind of going like this, right? It's kind of bigger and bigger spiral kind of thing, right? So is the acceleration different depending on where I'm looking from? Yes. Okay. Which frame should I pick? Where should I look at it from? Let's say I'm on Earth. Where do I look at it from? Should I pick the frame on Earth? Should I pick the frame attached to the spider? I mean, to the spider. Should I pick a frame attached to the Frisbee? Which one should I pick? Where should I be looking at it to do this F is equal to ma? Because obviously the accelerations are different, right? A frame attached to the spider sees no acceleration whatsoever. Right? Okay, this is irritating. So, which frame should I pick? Come on, let's warm up. We have another 15 weeks to go. We're going to be doing a lot of talking. That's excellent insight. So you got to pick some frame, because if you pick the Frisbee, then you're ignoring some things, right? So which frame should we pick? That's exactly right. But which one would you pick where you wouldn't have to add anything? Which one? The Earth? What do you think? The Earth? But isn't the Earth moving? What?
But the Earth's movement is affecting the Frisbee and the spider and everything that causes people, so it doesn't really matter for this.
But that's true of any frame. But I mean, you're actually on the right track. Shall I tell you the answer? The answer is actually, you pick an inertial frame. Remember that word? But there is no such thing as an inertial frame, really. Okay? What it means is it's a frame that is motionless in space. And the Earth moves with respect to that frame, and the Frisbee or the space shuttle moves with respect to that frame. And you need to calculate the acceleration with respect to that frame. But it turns out that the relative velocity, the relative motion of the Earth with respect to an inertial frame is much lower compared to the relative velocity of the space shuttle. So we can just pick the Earth. Get it? So it's actually an approximation. So we're just going to pick the Earth. Right? Because space shuttle moves really fast on the Earth. So if you actually picked the inertial frame, it would make such a big difference. So from a dynamics point of view, we pick the Earth because it's an inertial frame or an approximation of an inertial frame. But from a kinematics point of view, we don't care what an inertial frame is. An inertial frame is simply the frame in which F is equal to ma. Right? What we're going to concentrate on now is calculating the A in whichever frame you choose. Get it? It just so happens when we start writing dynamic equations, by the way, the adjective is dynamic or dynamical. They're both correct. Okay? It took me 20 years to figure this out. But anyway, from a kinematics point of view, we should be able to figure out the velocity of anything with respect to any frame. Right? And then, when we come to dynamics, we'll make sure we do it with respect to an inertial frame and write F is equal to ma. But right now, our focus is on the A. All right? So let's figure out how to calculate the velocity of and the acceleration of the spider with respect to different frames. And we know, by the way, that the Earth is the frame we really care about. But we don't care in kinematics, right? Because kinematics is all motion. We don't care about it. Okay. So what's a frame? Let me start by asking you to guess, and then I'll tell you what it is. What's a frame?
Perspective.
Yeah? It's a perspective. Any other words for it? I'm actually holding a frame. Here's what a frame is. When in doubt, imagine a frame to be some sort of three-dimensional transparency. Okay? Now let's limit ourselves to two-dimensional space. A frame is a transparency. That's all it is. It is this imaginary set of points that are kind of rigid with respect to each other. Get it? So here's a frame. Let us say that I say that, we'll draw it here. This is the corner of the room. Okay. And this is the Frisbee. Now I can attach a frame to the Frisbee as well. Okay. Now let me remove this. I'm going to call this guy frame F for Frisbee for the time being. And every point of the transparency moves kind of rigidly, and that's that frame. That's frame F. Get it? I used a capital letter F. I put a circle around it. I put a squiggly line, right? And I called it a frame. So this is the frame, right? And this is, let's call it Earth, E, right? So let's call this planet Earth. where most of us live. And so this is the frame attached to this Frisbee, right? It can turn, it can move, whatever, right? This is the frame attached to the Earth. Right now it's stationary, and this guy's moving with respect to this. Got it? So with respect to the Frisbee, oh, by the way, now we have an insect here, the spider. Let's call it S. And it's kind of heading out in some direction like this, right? So with respect to the Frisbee, if you're sitting on the Frisbee, F is frozen, right? So all you see is the spider kind of walking away. But with respect to the ground, or the Earth, E, right, S is doing all sorts of funny things, right? So that's what a frame is. So now with that, let's jump in and get a little more detail. I'll use transparencies once in a while, but I'll really be doing chalk and talk, right? So you need to stop me. I'll have my back turned towards you. You need to stop me if you have any questions. I'll put this away. In future, by the way, if you don't mind, what's your name? I'm sorry? Carly. If you don't mind, this thing being right next to you and it's hot, it's okay. But if you do, leave that chair unoccupied. All right, I've learned one name, Carly. Getting there. Another 129 to go. Okay, so let's start the actual, the serious portion of the class. So I said a frame was basically a transparency, okay? And that's the best way to think about it. And a frame is essentially, in 2 dimensions, a rigid imaginary set of points that are rigidly connected to each other, okay? Like the transparency. It doesn't mean there's any stuff there. Is an actual rigid body a frame? Anybody? Yes, no, maybe, sometimes. Yes or no? Yes. Yes, it is. It just happens to be a set of points where there's mass on a frame. Get it? That's all there is to it. A rigid body is a set of points where there's mass. So a rigid body can also have a frame embedded in it, and in fact it is kind of a frame. It just has a mass, right? Okay, so let's start. A frame is a rigidly connected continuum of imaginary points. All right? Now, one of the things I did was in that frame, I picked 2 little vectors, right? 2 vectors. You know what those vectors are called? Those little 2 vectors I put. Yeah? Yeah, you could say axes. You could even call them unit vectors, right? But the technical term is they're basis vectors. Okay? So I can identify a frame, that transparency. I could take the bottom left corner and put 2 little unit length vectors at the bottom left corner, right? And that becomes the basis vectors of the frame. I pick them once. I can pick any 2 mutually perpendicular vectors. I don't even need them to be mutually perpendicular. They just shouldn't be parallel, right? But for convenience, we pick 2 mutually perpendicular little vectors, unit length, and we call them basis vectors, right? So we can embed 2 mutually perpendicular unit vectors which are frozen for that frame, right? Once and for all, and call them the basis vectors. Okay, so what that means is that I could take, I erased it. You know what, let me keep that down until I finish my demonstrations. I could just take in this case, for this frame, right? For this frame, the edge of the transparency is here. Can you see it? Let me see. Can you see it? That's the edge of the transparency. I could have picked a little unit vector along, the horizontal, a little one along the vertical, and call them the two basis vectors of that frame. Doesn't matter where I pick them? No. I can pick any basis vector, right? So I'm going to pick them here. And I want to give you a little convention. I'm going to refer to them as little f1 and little f2. The underscore indicates that it's a little vector. Okay? Now, I can similarly take Earth, planet Earth, where most of us live, and call this E1 and E2. And this is my little convention. Right? I'm going to limit my descriptions to 2 dimensions, but everything I tell you about in kinematics easily and seamlessly translates to 3 dimensions. That's the beauty of the way we do it. Okay, so we'll do everything in 2D, but you just go to 3D, everything's fine. With cross products, dot products, everything will be the same. Okay? So these are the basis vectors in the unit length. And now, so any vector with respect to frame F can be, using these basis vectors, can be expressed as, something times F1 plus something times F2, right? With respect to these basis vectors, that'd be something times E1, something times E2, right? I might come back to this. Okay, let me ask you a question. So let's say I pick a frame, F1. Oh, sorry, F. And I take a vector R. It's a little unit, it's a little, vector, and I freeze it in that transparency. I draw it. Can it ever change within the F frame? If I draw it there, right, and I'm sitting on F frame, will I ever see change in length or direction? No. But that same vector, if I'm sitting in the E frame, I'm moving the transparency around, will it change? Yes. Right. Will the length change? No. But what will change? Its direction will change, right? So that means that a vector embedded in a frame will not change in that frame, but with respect to some other frame, it might change. Okay? All right. So here's what I'm going to say, and then I'll explain this more. By the time we're done with today's class and next week's class, you'll understand this completely, because we're going to do this in gory detail. Okay? But bear with me. We're going to make a few leaps here, but when we're done, you'll be completely, totally copacetic with it. Oh, sorry, misspoke, miswrote. By the way, I haven't said anything profound yet. Everything is very intuitive, right? I haven't said anything special, so you're not missing anything. I'm just going slowly. We'll gather speed in a minute. And I'm going to say this I'm going to say what I just said in English in a slightly more mathematical way. Okay, so now I'm going to write something for you which might seem a little odd, but this is the thing you need to get. Once you get this, all of kinematics is a breeze. D by dt of a vector fixed in a frame. Let's consider frame F. Give me an example of a vector that's fixed in frame F. Actually give it to me in terms. Make up a vector that's fixed in terms of, B1, B2, F1, F2, in terms of frame F. It's an odd question. Yeah, huh?
Vs.
Vs is the velocity, right? It could be fixed. Let me just tell you. Is this vector fixed in frame, this is F. Is vector F1 fixed in frame F? Yeah. What about this vector? Is this fixed in frame 1? Yes, right? So any vector which can be written as, in terms of the basis vectors and constant numbers, is fixed in the frame F, right? So any vector R that is fixed in frame F, I'll just call it R right now, where R is fixed in F. Here's what I'm going to say. D by dt of that R is equal to 0. I haven't told you precisely what this d by dt is. I'll explain it to you, right? But you know that that vector, if it's fixed in frame F, if I take the derivative, it should be 0, right? It ain't changing. It isn't moving, right? Now, if I take this derivative of that same vector, not in the frame of the Frisbee, but in the frame of the Earth, is it going to be 0? No. So I need to have some way of saying, listen, I'm taking this derivative in frame F, not in frame Earth, right? How would I denote that? Very good. So for example, I could put a parentheses and a little f like this, right? To say, listen, I'm taking the derivative with respect to frame F, right? I could do that. But it turns out that a better convention is to simply write the frame of reference here. Okay. So when you see something like that, this is the way to read it in English. The derivative of vector R with respect to frame F. And if I tell you that derivative, that R is fixed in F, the statement I'm making is that derivative is 0. Got it? Make sense? Any questions? I insist on at least one question at this point. I get tired. I need a break. Anyone? Yes. Thank you. What's your name?
Rachel.
Rachel.
Is that 2 lines or 1 under the F?
Is that what?
2 lines
Under the F. That's actually just, wasn't even meant to be a line. It's not a vector. It's just a frame. So it's just a capital letter. Thank you. Right? F is just the name of a frame. I could call it Rachel. Right? Rachel, right? Yeah. So I could call it Rachel. I just called it F. Just a name. Okay. Any other questions? Anyone else? It's oppressive in here. We should call facilities and figure out how to turn the air conditioning or open the window or something. So if you remind me, I'll call them later on. Thanks. Okay, so that's all there is to frames when you look at one frame. And now the fun starts, because now we're going to start looking at taking derivatives and looking at stuff across frames. All right? And once I do that, we'll jump into the Frisbee problem, we'll nail it. It's a 10-10, about 10-5. We might not finish the Frisbee problem. We'll certainly set it up and start doing some of the math. And we'll finish it off worst case next class. Okay? Okay, so now let's look at multiple frames. So, I'm going to call it multiple, but we'll always look at pairs of frames, 2 frames. Right? And if you can do the math across 2 frames, 3 frames is just a chain of 2 frames. Right? So we'll just look at 2 frames, but we'll call it multiple because it goes to multiple. Okay. So imagine one transparency, or one frame, which is planet Earth. attach a basis vector to it, or basis vectors to it. E1 and E2. Okay? Now let's think of another frame B1, I'm sorry. Actually, we called it F for Frisbee, right? So we'll call it F. What are the basis vectors in F? F1, F2. Okay. First question. Can you write E1 and E2 in terms of F1 and F2, or F1 and F2 in terms of E1 and E2? Yes. What do you need to tell me what E1 and E2 are in terms of F1 and F2? The, starts with an A, the angle, right? So, now one of the things I'm going to do in this class, especially because we're going to do a lot of stuff and I want to keep you guys engaged, is I'm going to have these snap quizzes. Ajay may have explained the snap quiz to you. But the way the snap quizzes work is we look at them and we make sure you put in some effort, and we absolutely don't penalize you for making any mistakes. In fact, we penalize ourselves. We don't penalize ourselves, but we, you know, we see what we succeeded in transmitting. All right. So here's what I want you to do. And some of these snap quizzes are it's not like we're asking you to recall something. We're actually asking you to look ahead. Here's a snap quiz. I want you to write for me F1 and F2 in terms of E1 and E2, assuming this angle is theta. And this is basic trigonometry. Yes? Pull out a sheet of paper, write your name on top, and have a go at it, and we'll collect it at the end of class. Yes, sorry. The angle is the, very good. So let me explain. I have defined theta. I could have defined it any way I could, you know, because I'm the professor, I can do what I want. You know how it works. But anyway, it's the angle between F1 and E1 at a snapshot in time, at an instant in time. I'm calling it theta. And I want you to tell me what F1 and F2 are in terms of E1 and E2 as a function of theta. Yep. F1 and F2 are both unit vectors. E1 and E2 are unit vectors. Okay? Yeah, I want you to write something like F1 is equal to something E1 plus something E2. F2 is equal to something E1 plus something E2. That's what it'll come out looking like. And it might have a few sines and cosine thetas floating around. In fact, it better have some sine thetas and cosine thetas, right? A handout. Has it been put up yet, Ajay? Will the kinematics PDF file? We'll put it up like today or tomorrow, which explains all this. All right? I'll tell you about the book in a minute when you're done with the quiz. Yep.
It's just F1 equals to cosine theta E1.
Hold that up. Okay, well, yeah, good. Yeah, I get it. I know it's easy. Good. I want you to know it's easy, but I want everyone to know it. Good. What's your name? Joe. What's your full name? Joe?
Khoury. Khoury.
Khoury. Excellent. Only because Joe is a common name, so you know. There's a dean at MIT. I think he's still a dean, right, with your last name? Yeah, Phil Curry. Okay, everyone done? Another 90 seconds. It doesn't matter if you don't get it. Once I write it down, you'll get it. I want you to put in the effort of trying, that's all. I tell people that with things like this, it really helps to grit your teeth. It doesn't really, I'm just joking. Got it? Got it? Okay, 10 seconds. Alrighty, we're done. Anyone? Joe, what's F1 and F2 in terms of E1 and E2?
So F1 is cosine theta E1 plus sine theta E2. F2 equals to minus sine theta E1 plus cosine theta.
Did everyone get this? Yeah? They would automatically be, yes, they should. Think about it, right? No, think about it. So the question, so first of all, let me come back. It's a great thought. Hold that thought, right? Do people agree with this? Ajay, is this correct? Ajay is the TA. He wasn't looking. Okay, that's fine. Let me look at my notes and confirm. Okay, F1 and F2. That's correct. Excellent. Okay. So what's your name? How do you spell it?
R-A-N-E.
R-A-N-E. Excellent. Rain. So the question Rain is asking is, look, F1 and F2 are unit vectors. E1 and E2 are unit vectors. I'm assuming this is what you're asking. So obviously this better be a unit vector, right? But as it turns out, if you transform between unit vectors, what comes out will end up being magnitude 1. And the reason is that if you take the magnitude of this, you get cosine square theta plus sine square theta, which will be 1. So it'll kind of self-normalize. Get it? Did people understand what I just said? Right? So this is correct. Any questions about this? Does anyone want to know how I got this? It takes a lot of courage to say yes, and I'll show you. You want me to show you? Okay. It's very simple, right? If you think of it the following way. I'll do it below, all right? Oh, I'll do it here. By the way, this is a terrible classroom. I apologize. So if you can't see stuff from a distance, just call me and I'll try and make it bigger. So F1, right? F2, and we're trying to calculate F1 and F2 in terms of E1 and E2, right? So the way we would do it is, there are a couple of ways to do it. One is you can just take components and add them up, right? So one of the things you could do is you could say, listen, F1 is composed of this component of E2 and how would I do it? What's an easy way to say this? Yeah. Or yeah, I could do the other way around, right? So I can take the projection of F1 on E1 and take the projection of F1 on E2. Get it? What's your name? Erica. Right. I can just take the projection of F1 on E1 and E2, right? And just use these thetas, right? And then take the projection of F2 on E1 and E2, and then write out. That's what you'll get. Okay? I don't want to do it only because I I can show it to you after class. It's just very basically just add the projections, and you'll get that. It's in the notes. Okay, what is E1 and E2 in terms of F1 and F2? What's a quick way to do this? Yeah, you could solve it, or there's another way to do it, which is if you put yourself in F1 and F2's, if you kind of turn it around, it's like replacing theta with a minus theta, right? So if you replace theta with the minus theta, what you'll get is got it? So this is how you go back and forth between two frames, and as long as you know the angle between the frames, right? Now here's the deal. If this frame is rotating with respect to this frame, the theta will change. But at any given point in time, if you know what the theta is, bingo, you can calculate F1 from F1 and F2 in terms of E1 and E2, and vice versa. Okay? Any questions about this? Yep. Yes. You will, but it's many more steps, so we'll come to that. We'll nail the spider now. All right? Okay, but this is how you transform between frames. Okay, so now the notes go. There they are. Okay, now I'm going to tell you something which will seem like an empty trick, and then we'll do the spider problem, and it'll make sense. Now, let's assume that we have some vector R. I'm trying to thread the needle here. I'm just thinking whether I should give you the conceptual point first. Okay, let's just jump into the spider problem, and then because a lot of people asked about how solving that, getting the velocity. Let's just do that now, and then I'll make the final point I want to make after that. Okay, so this is how you translate between frames. This is how you transform between frames, and we're all set. So now we have all the math we need. There's one little trick I want to tell you, which I'll tell you now in the context of the spider problem. And now what we're going to do is actually try and figure out what the velocity and acceleration of that spider are. All right, so let's do that. Okay, so this is the corner of the room, right? This is the room, and in the corner of the room, I have two unit vectors. Let's make them a little shorter. These are too long, right? We'll call them E and F, just because we've been using that for Earth and Frisbee, right? E. And this is our Frisbee. We call that F. And it's spinning. We'll call these F1 and F2. So, first question to you folks. The first thing you need to do, by the way, actually as a comment, is when you draw a picture like this, you must always go out of your way to label points that are of importance. So, for example, this point, we'll call it P, right? It's just a point P. I could have called it C, center of the Frisbee. Let's call the position of the spider S. Now, have I lost any generality in claiming that the spider is along this unit basis vector? Have I lost any? I haven't, right? Because I picked them arbitrarily. So I might as well just pick that. Okay. Let us call, now, actually even before that. So here's a question to you. How do I parameterize the position of the spider at any given moment in time? What do I need to know to tell you where the spider is right now? Say it loudly. The relationship of F1 to reference frame E. And what would that relationship be? Think about it. What do you need to know? Excellent. Okay. So one parameter you need for sure is this angle, right? Which is theta, which we just used up there. What else do you need to parameterize? If I want you to give me the exact coordinates of the spider, what other numbers do I need? Yep.
How F is moving with the way to
Now, if I know the angle, but I know it is a function of time, then that's one parameter. What are the other parameters I need? Don't think of motion yet. Just think of like a snapshot, right? Just give me distances. We'll get to velocity, right? See, this is what I want you to think through. Velocities are derivatives of location. So go ahead.
So distance?
Exactly. So what else do we need? We need the distance of this point P from some point embedded on the Earth. It doesn't matter which point we pick. We need to pick one point that's embedded on the Earth, right? So I'm just going to pick one point at the corner of these two where I've drawn these axes. It doesn't matter. I could have picked it here. I'll call that point O. So this distance, I'm going to call it U. And what else do I need? It's 2 dimensions. I need the vertical distance. I'm going to call that V. What else do I need? Come on, quick. Excellent. I need this distance. And I'm making this up as I go. I'll call that L. Okay? Now, and this is something you should do every time you solve a problem like this. What is the position of the spider with respect to that point we picked on the surface of the Earth, which we call O? Anybody?
L cosine theta.
Okay. So watch this. I'm going to call it R. Hold that thought. Okay, I'm just going to write it out first. The position vector from O to P, which is the vector, this vector, right? That vector. Get it? Right? Is equal to ROP is equal to what? Go ahead. Well, no, keep going. U plus
L cosine theta.
But don't I need some L cosine theta? Right. Yeah. Okay, you're going to write like this. U plus L cosine theta E1
Plus V times L sine theta. By V.
Okay, that's perfectly correct. Yep.
It's not on.
I'm sorry, that's S. Yeah, the position of spider. Right, that's what he wrote. I beg your pardon. Right? So that's exactly correct. Say it again.
A V.
That should be V, yeah. Okay, so you actually, that's perfectly correct. You did it right. But now I'm going to give you a slightly different way to think about it, which will lead to the same answer. You did a shortcut in your head, which is brilliant, right? But now I'm going to give you a different way to think about it, which is a little more methodical, but which also brings out the point I want to make to you. I'm going to write this differently. That was right, but I'm going to write it differently. I'm going to write this vector ROS as equal to, because I'm not as smart, ROP plus RPS. Is this fair? I can do that, right? Break it down into 2 pieces. Now, then I'm going to say ROP is simply U E1 plus V E2. That's this guy. Is that correct? Am I going too fast? Do you see what I'm doing here? Everybody? Yeah? And what is RPS? And here's the rub. I'm going to write it as, get this, L Does that make you queasy? right? Makes you queasy, right? It's like putting, strawberry ice cream on a cheese sandwich. Yeah. My daughter did that actually this morning. So here. Oh, I'm sorry. That's probably what made you queasy. I mean this way. Now, does this make you queasy? No, it doesn't make you queasy. That should still make you queasy. Think about it. Anti-mixing bases. Is that okay? Can I mix bases? Yes, no. Okay, all in favor. All against. Okay, I set the all against up. I was misleading you. It turns out, no, it's my fault because I wanted to kind of expose any hidden latent queasinesses. Right? It's okay. It's okay to mix bases. Absolutely okay. Yep.
Define them up there in terms of each other.
Yeah, well, it's okay because even if I didn't define them, it's a vector, right? I can add vectors. It's perfectly okay. Even if they're different bases, that's okay, right? So what you did was you kind of down-converted everything to E1 and E2, right? But I'm taking the lazy approach, which is I'm going to write them like this just because you'll see in the class certain things come out if you write it this way. But what you did was perfectly right. In fact, I'm going to do what you just said in a moment. Now, here's the deal. What is the velocity of the center of the Frisbee? First of all, that's an incomplete question. I haven't told you everything you need to know. But what's the velocity of the center of the Frisbee? What? I can't hear you. No, you might have said it right. I really couldn't. Everyone spoke simultaneously, so you need to speak louder. What was incomplete about the question I just asked? I said, what's the velocity of the center of the Frisbee? Yep. I didn't tell you a reference frame, right? So, what's the velocity of the center of the Frisbee with respect to planet Earth? Yes? Yeah. So, this is how I'm going to write velocity. With respect to planet Earth, E, right? The velocity, V, of which point? P. Right? This notation is very important. If I just say the velocity of point P, it makes no sense because I could be asking the velocity of point P with respect to the Frisbee, which would be 0, right? Right? So the velocity of point P with respect to Earth is equal to d by dt of Rp. Is that complete, or am I missing something there? Anyone? Someone in the back, someone in that quadrant. The way I wrote d by dt, am I missing something here? Yeah. I need to say, from here on, when you take a derivative, which we still need to completely define, I need to tell you which frame I'm taking the derivative with respect to. Okay? And I should have written ROP. I'm still a little rusty. I've been gone for the summer, so I'm making mistakes, but you caught me. That's good. Yep.
Why do you need the second with respect to frame E?
Why do I need the second? This one? That's a beautiful question, and hold that thought, and remind me if I don't get back to it. That's a great question. Okay? But you can see that it doesn't hurt to write it. It's complete. It turns out that if I flip the frames, it might look correct, but it'll turn out to be wrong. Okay? Well, what's your name? Sam. Sam? All right, I'll remember that, and we'll come back to that. And what is the velocity of the spider? How to write the velocity of the spider with respect to the Earth? Quick. E Vs is equal to? Come on. E dt, let me raise this, of R OP, or S, which is the same as E d by dt R OP plus E d by dt R PS. Right? So I've done nothing differently than what Sam did, but I'm just doing it in a more painstaking way, that's all. Nothing special. Okay, I'm going to raise this up there and go back to these boards and finish up. This is very simple stuff, so you're not missing anything if you feel like, what's he doing? I know this. It's okay. I'm just doing it simply. Nothing profound. Okay, so we're picking up here. Okay? So let's go directly to this guy. Let's analyze this guy. I just broke it out there for you just to kind of get you to walk through it with me. I'm going to expand on that. So I'm going to take first this term. Okay? Okay. E d by dt ROS. And what is ROS? It's UE1. Sorry, ROP. Right? This is ROP. It's UE1 Okay? Yes? What do I do now? Yes? That's an equal to. No, that was a kind of a stroke. I'm writing like this. It's kind of hard. I'm trying to save Blackboard, but it wasn't a negative. Okay? Is this good? So what do I do now, folks? I'm simply trying to calculate this term. What do I do? Very painstakingly. I'm doing very slowly and painstakingly. How do I take the derivatives and the vectors? What do I do here? Say it again?
E1 and E2 are constant, so you can pull those out.
Exactly.
U and V shouldn't be constant.
Exactly. Nailed it. All right? So I could think of it as two ways. One is I can do it by parts, right? So I can go E d by dt U times E1 plus U E by dt of E1. What is E dt of E1? 0, right? That's what a constant is, right? So this corresponds to simply get it? Everyone good with this? Yes? Okay. So that's that first term. We just nailed this guy in excruciating detail. Now let's write this guy out. Is equal to what? Help me out here. So what do I do here, folks? Is F1 constant in E? Yes, no? No, right? So strictly speaking, I'm in a bit of trouble here. So what do? Sam did that actually, but he did it intuitively, he was right. What should I do? Yeah, exactly. So let's write it in terms of, our wonderful transformation there. Those transformations are very important, by the way. You need to nail them, understand them, okay? And put them in your crib sheets. If in the exams, we permit your crib sheets. There are only 2 or 3 formulae that are important. And that's kind of an important one, these transformations that we had down here. Those guys. Okay, so these you should remember and understand them. Don't make mistakes there because they cascade and screw everything else up. Okay, so that is equal to, expand it for me because I can't see it from here. Please. Come on. plus, sorry, okay. I want to raise that and finish it up here. We're still calculating velocities, right? What did I do wrong? Oh, okay. I thought, let's see. I can't see it from here, so I've F1, yeah. They were backwards, thank you. Okay. So what do I do now? Chain rule, right? So I just take the derivative. And this is what it'll come out to be. It'll be, is L constant? Is the theta constant? Is the E1 constant in E? Yeah. So it's going to be in parts. Actually, I'll let you guys do it. Why don't you do it and read it out to me? Do it in parts, like I was trying to do it there. I don't want to just write it out and, I want you to read it out to me. Take this term, right? Use the chain rule, and tell me what it's going to come out to be. Yes?
E1.
What's her name?
Amanda?
Amanda?
Yeah.
Yeah.
E1 in parentheses times L dot cosine theta minus L sine theta.
And then anything else?
Sine.
L sine theta. That's it?
Yeah.
Is there a theta dot?
Yes.
Yes. Very good. And then?
Plus E2 times L dot sine theta times theta dot L cosine theta.
Make sense? Right? So here's the trick. When I write vectors like in this way, it's perfectly reasonable to do this. E1, E2, and then I put in an F1 here, right? And I said it should make you feel queasy. It shouldn't really. That's okay. It's okay, but when you take the derivative of this guy with respect to a frame like E, the first and cleanest way to do it is to down convert all the kind of contaminating terms which are not E1, E2 bases down to E1, E2 bases. Get it? And then take the derivative, because even in E2 bases, the basis vectors are constant in E. If you just do this, if you take the derivative of F1 by itself, then you have to figure out what it is, and you'll end up converting anyway. Get it? So the bottom line is that we've just computed that R PS is this. So the velocity of the spider, when you put it all together with respect to the Earth, right, which we write as E spider with respect to the Earth, is equal to, now add it all up and tell me, please. What? Yeah, that's d by dt. What? Okay, what is this? What is the velocity of the spider with respect to the frame E, the Earth? And that, my friends, is the velocity of the spider with respect to the Earth. Okay? And that's the cleanest way to do it. And we use no magic, right? We use frames and a very basic geometric transformation between frames, and we calculate the velocity. That's it. There's no magic to it. It's painful, and when we get an acceleration, it's going to get even more painful, trust me. We're going to calculate the acceleration now, right? But that's what it is. So, any questions about this? And if not, we'll set up the next point. Any questions? I insist on at least one question at this point. I'm out of breath. Anybody? Totally get it? Okay, then I have a question for you. How do you calculate the acceleration of the spider? By the way, actually, let's take a minute here and just appreciate what we've done here. If the Frisbee were not translating, okay, which terms would vanish? So let's say I was spinning the Frisbee around my finger, right? This would go to 0, and this would go to 0. Okay? And you know what this term, the rest of it will turn into? It'll be some sort of theta dot L term. Theta dot L. Does it make sense? Theta dot L? Right? This is the vector equivalent of theta dot L. Get it? Right? It's actually omega cross R. That's what it'll come down to be. Omega cross the L vector. Right? We haven't done any cross products here, by the way. But you can see how it came out, right? Does everyone understand what I just said to you? Right? Okay, what if the spider were at the center of the Frisbee and not running away? Which terms would vanish? L dot would go away. What else? And L would go to 0. Right? So what would the velocity be? Simply translation. Makes sense, right? Right? So this is a composition, it's an addition of the translation velocity and the kind of the rotational aspect. Right? So, you know, from basic physics, you kind of see it makes sense, right? Yes? Okay. Now what we're going to do is calculate the acceleration. And now we get into no nonsense, you know, vector derivatives here. But there's no magic either. It's just painstaking stuff. We'll introduce the subtle stuff in a minute, actually in the next class. So, how do you calculate the acceleration? Yep, that's it. No magic to it. Just take the derivative of the whole thing. So let's do that. Because, you know, we're MIT, right? We don't do kind of stuff. We do it. All right, let's do it. So, let's see. E acceleration A of spider S is equal to d by dt. I'm sorry, I'm writing it small here. Of E velocity S is equal to. Okay, let's start at this term. What does this term become? So let's put an E1 here because E1 is constant. U double dot, yeah? Keep going.
Plus L double dot.
Keep going.
Minus L dot.
Keep going. Come on. Huh? Did we miss a term? Is that correct?
Minus theta dot. Minus theta dot L dot.
Hold on. That should give us 3 terms, right? So it should give us the L double dot term, right? The L dot. Are we coming to this one now? 2 terms. I'm sorry. Okay, yeah. So go ahead. Sorry, but I interrupted you. Go ahead. Yeah. Someone was reading out the next term to me. Go ahead.
Minus theta dot L dot.
Uh-huh.
Sanjay.
See, I don't have my notes in front of me. I'm right next to the board, so you need to help me out here. Yeah.
Minus
Okay, is everyone in agreement with this? Huh? Okay. Everyone in agreement with this? You did it. I didn't do it. Okay. That's the first term, right? Plus E2. Anybody? Someone else? Someone back there? Just then L double dot sine theta, okay. Try and keep it in the same pattern, okay? Because I'm trying to pull out a pattern for you here. Yep, keep going. Plus. And then plus or minus? Next. Minus theta double dot. Plus. Okay, theta double dot. Okay, two more terms, nearly there. Plus theta dot L dot cosine theta. No magic, it was just pure hard work. Just took the derivative of that. And we calculated the acceleration of the spider. Okay? And what you just did encapsulates 300 years of physics, believe it or not. And there are famous names attached to some of these terms. And I'm going to give you those names now. And I said it to the last class, and I make the same promise to you guys. If we came up with a term here that the other physicists have missed, I'll name it after the person in the class who came up with this. Right? So for example, some of these terms are called Coriolis terms. So we'll call it the Rachel term if you came up with that. Okay? All right. So let's examine this. So this is the vector form of it, right? What is this? Kind of in English? Translation acceleration, right? Translation. Okay. Of the Frisbee, center of the Frisbee, right? What is this capture, kind of in English? Of, with respect to, yeah, in English, that's kind of what this is. This is the spider kind of, right? This is spider. Spider term. Okay, these are kind of informal terms, but I'll formalize them later on. Spider translation. Okay. Anyone recognize this term? Yeah. And that's called the centripetal acceleration. Get it? Remember theta dot squared? Ring a bell? Theta dot squared, right? Spin something, kind of accelerates inwards, right? L theta dot squared. Hey, there's an L theta dot squared. Sine theta cosine theta, so that's the vector form of it, right? So that's centripetal, right? It's named after a famous French engineer by the name of Centripetal. I'm kidding. Centripetal, right? No, centripetal. Okay. Anyone, does this term kind of make sense? What's that? Yeah, it's the angular acceleration multiplied by the force arm, right? But again, written in vector form, right? Does it make sense? And that is actually, for some reason, called the Euler acceleration. And then we have two guys left out. Anyone remember what those are called? Yep. Coriolis. Here's the deal. They're just two straight terms. If you do the math right, they show up. We did the math right. They showed up, no surprise, right? Now, actually the funny thing is, you see it's minus L dot theta dot. It's the same term twice, right? So I can actually make this 2, right, and remove this. And it's the same term twice here. I can put a 2 here and remove this. It's the same thing. I just am consolidating terms. And there was this French engineer by the name of Coriolis. He found, I think the history is that when you shoot a projectile from a ship or from any vehicle, but usually ships, in the northern hemisphere, I think gunners found that they were missing to one side and they had to kind of compensate. And once the gunners perfected the skill and they crossed the equator, they found that their skill was useless because they would go to the other side. And the straight term is referred to as the Coriolis acceleration. Okay, this is also the reason hurricanes spin one way in the northern hemisphere and another way in the southern hemisphere. We'll talk about all this at the beginning of the next class. But what you've just done with me is from ground zero, using the most basic geometry, you have derived terms that go back 300 years, or took 300 years to derive. So this term, this collection of terms, is called Coriolis. And this is the most general statement of the calculation of acceleration that you will need in kinematics to compute the motion of complex systems. And now if you have, now look, we can do frame E to F, right? Let's say the Earth's spinning and there's someone watching us from another planet. Well, no problem. You can kind of compose it and you can compute the acceleration with respect to that planet. The math will get hairy, but there's nothing profound. Get it? Questions? All right, we'll see you next class.